Hi guys, this is Diveflyfish. Just want to show you something. Just been doing a little reading on the Faraday disk type phenomenon, and it occurred to me that one way to show the importance of the spin intrinsic to the magnet itself and why angular momentum, when these fields are being hit in certain directions, counter-rotating or otherwise, with gizmos such as the ostensible mechanism of action for the Glock, etc. Is there any way to show that it's an intrinsic phenomenon to the spin of the magnet itself? And I think what I can show tonight is that this neodymium magnet on this side and this neodymium magnet on this side are in direct fluid intimate contact, meaning in a conductive situation, such that we have a north face on this aspect and a north face on this aspect, and the combined south faces are internal right here. When the Faraday disk is being rotated in such fashion, if I take a measurement on this north face and the central shaft, we are achieving a current and voltage in a positive direction. And if I take a measurement on this north face and the shaft, I get a negative current and voltage reading. Yet this direction of the actual physical object remains identical. The only difference is that this is now a clockwise spin on this north face, and this is actually a counterclockwise spin on this north face. And despite the fact that they are in electrical contact with one another, it still provides a differential positive versus negative voltage in an ostensible homopolar situation, which I find sort of neat. So, in any event, for what it's worth, I'll show you the little experiment, but it definitely brings up the fact that you can have a charge separation irrespective of the intimacy of contact between two fluidly intimately contacting magnetic disks, which again gives one a pause in thinking about how the Glock may have functioned in a plasma itself as the conductive medium. So for what it's worth, just something to ponder. And again, this might be old hat to many people, and I apologize for being behind the eight ball, but I don't know if I've ever seen a scalar magnet situation being utilized as a Faraday disk itself. So if other people have tried this and have also found this to be the case, I find it fascinating. Now, another interesting experiment would be to have a larger version of this spinning in a sealed atmosphere of plasma while it's energized to see what would happen. It'd be fascinating to see what would happen in the plasma itself, because in the orientation that it is right now, you have essentially counter-rotating magnetic fields, and how that would affect the conductive plasma is intriguing. So for what it's worth, thanks for watching, and let me know what you think. And again, just to confirm what I'm talking about here, this magnet face is a north field, and this magnet face is a north face, and this central portion is south. So it's a scalar type magnet situation. Alright, there you have it. Hey guys, this is Diveflyfish. Just want to show you something. Been reading a little bit about homopolar motors, etc., and this is a little Faraday disk with a twist. Right here I have a scalar type magnet situation, so I have a south facing against a south facing, okay? And then this produces the scalar north, okay? So I want to show you something that's very interesting that definitely shows that the spin is characteristically important. So what I'm going to do first is I'm going to place one lead on the central shaft and then another lead on the top disk versus the bottom disk. And just know that, again, both the top portion of the disk and the bottom portion of the disk are, okay, this is the middle top portion here should be north. So we have north facing here, and we have scalar south here. So we have, again, north, should be north, north, and then south. Okay, so theoretically both sides are the same, but watch the microamperage, okay? Go for it. Go a little higher RPM, higher. Okay, so I take the reading, we're seeing a positive, a little faster RPM. Seeing a positive microamperage, okay? So you're seeing that as a positive microamperage. Now if I go on the opposite side of this, you see a negative microamperage. Yet we still have the same poles. So without question, it shows a very, very interesting difference in the spin of the magnet. So the actual spin face of the magnet, even though it's the same pole, as it were, the rotation does in fact make a very, very big difference. So again, this is the north face spinning in a counterclockwise direction, and this is the north face spinning in a clockwise direction, producing a differential in positive versus negative current flow, which I find somewhat fascinating. So, okay, now what we'll do is we'll switch this over to a voltage situation and see what we're seeing here in a direct current voltage. Now we'll start the motor up again, a little faster RPM. So we're seeing on this face here a positive microvoltage, and on the other north face a negative microvoltage. So again, current and voltage, even though the faces of the magnet are identical, meaning a north face and a north face with a south scalar, we're getting a differential in current based upon the rotation of the Faraday disk itself when it is a scalar magnet situation. So for what it's worth, counter-rotating fields, if they could be attained, it's understandable why that would be the case. So for what it's worth, hi YouTube, this is Diveflyfish again. Just want to show you, this is another situation where we have a little neodymium magnet here on a shaft to make a tiny little Faraday disk. Again, this is the north face of this magnet, and the opposite side is obviously the south face. So this is only one magnet. So we have north face here and south face here. Now, the interesting thing, unlike the scalar situation that I showed you here, where we have a north face against a north face with a scalar south, this has a normal orientation. So what we're going to do is we're going to spin this in the orientation counterclockwise in the same manner in way that we did with this one, and I'm going to show you a voltage reading on both the north face of this magnet and the south face of this magnet. So what we're going to do, and once I'm done doing that, then I'm going to shut the drill off, I'm going to reverse the rotation and show you the only way that I can get a negative differential voltage using either side of this disk is by reversing the spin of the magnet itself, unlike the scalar where you could achieve a negative differential even though you have the same north face here as you do here. So for what it's worth, I'll just show you. We'll start the drill up, and I'm going to take a measurement on the outside and the inside, and please keep a note of the current level. So we'll hit the drill, and when I take the current, you can see on this side on the north face it's producing a positive current. On the south face it's producing a positive current. So this is a direct current either side, south face, north face. Okay, now what I'm going to do is I'm going to reverse the polarity, or the spin of it, and we'll hit it again. And now we're seeing a negative current on the north face and a negative current on the south face. So for what it's worth, this is again in direct opposition to what we had with the scalar situation. So I just wanted to show you that as a comparison. In having a Faraday disk with a scalar magnetic surface that is in intimate electrical fluid contact with one another, and you still get a differential in voltage. So it's no longer a homopolar motor, as it were. It's a fluid intimate bipolar motor. So for what it's worth, just thought you might find this interesting. And there you have it. Another interesting thing to ponder with regard to the homopolar type situation is something akin to the Kromrey. Now, the Kromrey generator that I have has an armature on the inside just like this, which in and of itself theoretically could be turned into a Faraday disk if you so chose, and a measurement could be made from the axle to this. Now I did note that in this book, and again I just started reading it, there was a notation that, according to this one individual, the magnet should be in a radial and non-axial orientation as far as the disks that were spinning on an ostensible UFO. So in any event, if, let's say, the magnet, if this were a gigantic magnet, which it's not, it's just a large piece of stainless steel, actually magnetized in this direction versus radially magnetized. Now the interesting thing is a Kromrey is a radial magnetically oriented gizmo. What if we were to combine the Faraday disk phenomenon and the Kromrey in the same device by utilizing the massive current that is allowed vis-a-vis the Faraday disk in a Kromrey situation, as well as having the coils themselves. So you have an impulse, a radial impulse from a fixed magnetic stack, as well as a magnetic impulse that's imparted into this core, which would be somewhat of a self-amplifying situation, especially considering if you do this in a monopole or in a like against like situation, it might prove to be a very, very interesting phenomenon. So this is another thing that I wanted to bring up, something for other experimenters to think about, as well as imagine if this were a non-magnetic disc, which it is, it's stainless steel. You know, this is neodymium magnet, there's no magnetism there. Imagine if this were hollowed out and you had a flat sheet here, and instead of having stainless steel here, non-conductive stainless steel, you had a plasma, like a flat fluorescent tube as it were, and actually have the fluorescent tube plasma itself being subjugated by this radial magnetic field. What type of voltage differential or what type of current differential could we attain across this disk if this disk were plasma instead of being a conductive disk? So these are some things to think about, might spark some interest in experimenters. I think some more work needs to be done with the potential of combining gizmos. Any and all thoughts are welcome. So for what it's worth, the concept of utilizing a combination between the Kromrey and the Faraday disk as something that is worthwhile exploring. Thanks for watching.